a proposition, a statement that we've been talking about in previous or other videos, a statement of fact is a proposition, okay? And its truth value may be determined only either as a true value or a false value. There's no in between. Remember, we've discussed this. So when you say a rectangle has 4 sides, the truth value of this proposition is true, okay? If you say that the world is a cube, okay, this proposition, this statement, this sentence is actually false, okay? Moreover, when we're trying to work in this kind of logic, what we do is we assign linguistic variables to these statements. For instance, you could say that the linguistic variable or variable, simply variable, P means it is raining, and Q means I can carry an umbrella. So we can now relate those propositions to those variables and then play around with those variables. For instance, we can create compound statements by logically connecting those propositions. The most common connectivity between two propositions is an AND situation, okay? P and Q, okay? Or the most common one, another one, is an OR situation where you say P or Q, okay? Which is also called disjunction, and is called conjunction, it's up to you. And then the negation, which is called the not part. So these are some of those logical connectives that can be used to actually make compound statements and then reason about them. Look at the chart given here. We have tried to convey to you various logical connectives, the and the or, and the third one is implication, P implies Q, and the fourth one is if and only if, or you could say this logic tells you when both inputs are true, then the output is true, which is like logically that they are equality detector, it's called. Equality detector. It detects, this logical connective detects when the two inputs given to it are logically identical. So if you look at the AND, for example, AND means that both P and Q, the two statements, propositions, okay, if both are true, then P and Q will be true. Okay, that's the first row. Now, if I carry on in the same row, P or Q, which means if either of them is true, then P or Q will be true. As you can see, it's true. If you look at the third column, okay, in the first row, P implies Q. As you can see, we have P is true, therefore Q will be true, and that's what your implication operator connective will tell you true. The fourth, which is if and only if, or the equality detector, it looks at both inputs. So inputs are for P and Q, both are true, which means they are identical, they are equal. Therefore, this logical connective will give an output of true. Likewise, you can build the truth table for each of these. The first ones are very, very straightforward. I think I'll just give you a couple of more examples on the very last one, which is the if and only if. The equality detector. The third row, P true, Q false, okay? They're not identical. Therefore, output of the last column, the equality detector, they're not equal. Therefore, it's false. Then P is false, Q is true. Once again, they are not equal, okay? So equality detector will call it as false. And the fourth one, when both are false, the equality detector will say true. Yes, both are identical. So this gives you a true value when either of the two inputs are the same, both true or both false. And the rest are pretty straightforward. There are certain limitations as well. Propositions can only represent complete sentences. They can't go inside those sentences. Okay? They can't analyze the internal structure. And then there are no other quantifiers, where we say for all values of certain thing, this will happen. Or you say, if there exists some value which is this, okay? These are kind of quantifiers. We'll come across them later on. There's no particular representation available for this. So it's doesn't provide framework for proving statements like all humans are mortal or all women are humans, okay? There is no connections or logical derivatives that we can use to actually come to these conclusions. So this is a limitation of this representation power. Then the extension of this is called propositional logic, which is predicate calculus, okay? Where you have a predicate and we can use expressions like when you say the color of ball is green or blue, okay? You can represent it as color, bracket, ball, comma, blue, okay? So it's a concise and precise structural. You're going into the sentence and you're able to represent that statement or proposition. So relationship between the color, the ball, and the blue itself is actually quite obvious. Now, due to its greater representational powers, it provides mechanism for proving statements. And of course, can be used for logic manipulation. Remember, we can only represent facts that are either true or false. We can't have mixed values. And of course, then once again, the limitation is that can't represent complex sentences or natural language statements. So you could say, for instance, we can't represent the following sentence in propositional logic like some humans are intelligent or Ahmed likes cricket. You don't have it. That's where first order logic comes in. That's another representation, okay, which is sufficiently expressive and extension of the propositional logic. It's a powerful language that enables easier information representation about objects, and we can also represent relationships between these objects. So in first order logic, like natural language, it not only assumes that the world contains certain facts, statements, okay, propositions, but also assumes that you can represent, you have things like objects, you have relations, and you also have functions. So that's where you get the benefit of this first order logic. So objects like A, B, people, number, colors, cars, so forth. And relations can be, one-on-one or multi-unary or n-ary relations. Sister of, brother of, okay? A function, for instance, father of, best friend, third innings, and so forth. As a natural language, first order logic also has syntax and semantics. We will come across that when we come more detail. So some basic elements of the first order logic. There are several options available to us. We can represent constants like numbers 1, 2, 3. We can have names of cities, Karachi, Lahore. We could have name. These will be treated as constants. Then we have provision for defining variables, small letters, A, B, C, D, E, F, and so forth. We have the provision of defining predicates, right? Like brother, father, mother, sister, greater than, less than. And then we have functions also, square root, mean, max, minimum, and so forth. We can have connectives, as we discussed those logical ones, and or not, if and only if, implies, and so forth. We have equality, means two things are equal. And of course, the one that allows you to say things like for all values of, and also another quantifier which says if there exists. Now I imagine this is a lot of flexibility in terms of representation and manipulation of those propositions. I hope this was useful and you enjoyed. Thank you very much.